Why are the inner and outer planets so different? Local cosmic oddities. People have always marveled over the heavens and all that they hold, particularly now that technology allows us to view deep space. However, right in our own cosmic neighborhood, some fascinating oddities exist, things that just don't seem to make sense. One such oddity is the disparity between the outer and inner planets. The inner planets are small and rocky, low on moons, and entirely lacking in ring systems. Yet the outer planets are huge, icy, and gaseous, with ring systems and many moons. What could cause such strange, vast inconsistencies? Why are the inner and outer planets of our solar system so dissimilar? Through models and simulations, scientists are confident that we now grasp at least the gist of how our planets formed. We may even be able to apply what we learn about our own solar system to exoplanetary formation, which could lead us to understand more about where life might be most likely to exist. Once we understand the formation of our own solar system's planets, we could be a step closer to discovering life elsewhere. We do understand some of the factors that come into play for planetary formation and seem to create a pretty complete picture. Our solar system began as a massive cloud of gas, mainly hydrogen, and dust called a molecular cloud. This cloud underwent gravitational collapse, probably as a result of a nearby supernova explosion that rippled through the galaxy and caused a churning of the molecular cloud that led to an overall swirling movement. The cloud began to spin. Most of the material became concentrated in the center of the cloud, due to gravity, which sped up the spinning, due to the conservation of angular momentum, and began to form our protosun. Meanwhile, the rest of the material continued to swirl around it in a disk referred to as the solar nebula. The formation of planetary systems. Within the solar nebula, the slow process of accretion began. It was first led by electrostatic forces, which caused tiny bits of matter to cling together. Eventually, they grew into bodies of sufficient masses to gravitationally attract one another. This is when things were really set into motion. When electrostatic forces ran the show, the particles were traveling in the same direction and at close to the same speed. Their orbits were pretty stable, even as they were being gently drawn toward one another. As they built up and gravity became an increasingly stronger participant, everything grew more chaotic. Things started slamming into each other, which altered the body's orbits and made them more likely to experience further collisions. These bodies collided with one another to build up larger and larger pieces of material, kind of like using a piece of Play-Doh to pick up other pieces, creating a larger and larger mass all the while, though sometimes the collisions resulted in fragmentation instead of accretion. The material continued to accrete to form planetesimals or preplanetary bodies. They eventually gained enough mass to clear out their orbits of most of the remaining debris. The matter closer to the protosun, where it was warmer, was composed primarily of metal and rock, particularly silicates, whereas the material farther away consisted of some rock and metal but predominantly ice. The metal and rock could form both near the sun and far from it, but ice obviously couldn't exist too close to the sun because it would vaporize. So the metal and rock that existed close to the forming sun accreted to form the inner planets. The ice and other materials found farther away accreted to form the outer planets. This does explain part of the compositional differences between the inner and outer planets, but some dissimilarities still remain unexplained. Why are the outer planets so large and gaseous? To understand this, we need to talk about the frost line of our solar system. This is the imaginary line that divides the solar system between where it is warm enough to harbor liquid volatiles, such as water, and cold enough for them to freeze. It is the point away from the sun beyond which volatiles cannot remain in their liquid state, and could be thought of as the dividing line between the inner and outer planets. Ingersoll 2015. The planets beyond the frost line were perfectly capable of harboring rock and metal, but they also could sustain ice. Solar impact. The sun ultimately amassed enough material and reached a sufficient temperature to begin the process of nuclear fusion, fusing atoms of hydrogen into helium. The onset of this process spurred a massive ejection of violent gusts of solar wind, which stripped the inner planets of much of their atmospheres and volatiles. Earth's atmosphere and volatiles were delivered afterward and or contained underground and later released to the surface and atmosphere. This solar wind still flows outward from the sun now. However, it is lower in intensity, and our magnetic field acts as a shield for us. Farther from the sun, the planets were not as strongly affected. However, they were actually able to gravitationally attract some of the material being ejected by the sun. Why were they larger? Well, the matter in the outer solar system consisted of rock and metal just like it did closer to the sun. However, it also contained vast amounts of ice which couldn't condense in the inner solar system because it was too hot. The solar nebula that our solar system formed from contained far more of the lighter elements, hydrogen, helium, than rock and metal, so the presence of those materials in the outer solar system made a huge difference. This explains their gaseous content and large size. They were already larger than the inner planets because of the lack of ice close to the sun. When the young sun was experiencing those violent ejections of solar wind, the outer planets were massive enough to gravitationally attract a lot more of that material, and were in a colder region of the solar system, so they could retain them more easily. Moons and rings. In addition, ice and gas are also far less dense than the rock and metal that make up the inner planets. The density of materials results in a wide size gap, with the less dense outer planets being much larger. The average diameter of the outer planets is 91,041.5 km versus 9,132.75 km for the inner planets. The inner planets are almost exactly 10 times as dense as the outer planets. Williams 2015. But why do the inner planets have so few moons and no rings when all of the outer planets have rings and many moons? Recall how the planets accreted from material that was swirling around the young, forming sun. For the most part, moons formed in much the same way. The accreting outer planets were pulling in huge quantities of gas and ice particles, which often fell into orbit about the planet. These particles accreted in the same way their parent planets did, gradually growing in size to form moons. The outer planets also achieved sufficient gravity to capture asteroids that went streaking by in their near neighborhood. Sometimes instead of passing by a sufficiently massive planet, an asteroid would be drawn in and locked in orbit, becoming a moon. Rings form when a planet's moons collide or are crushed under the gravitational pull of the parent planet due to tidal stresses. The outer planets. How planets form. 2007. The resulting debris becomes locked in orbit, forming the beautiful rings we see. The likelihood of a ring system forming around a planet increases with the number of moons it has, so it makes sense that the outer planets would have ring systems while the inner planets do not. This phenomenon of moons creating ring systems is not limited to the outer planets. Scientists at NASA have believed for years that the Martian moon Phobos might be headed toward a similar fate. On November 10, 2015, NASA officials stated that there are indicators which strongly support this theory, particularly some of the grooves featured on the moon's surface, which may indicate tidal stress. You know how tides on Earth cause a rise and fall of water. On some bodies, tides can be strong enough to cause solids to be similarly affected. Zabritsky 2015. In less than 50 million years, Mars, too, may have a ring system, at least for a while, before all of the particles rain down on the planet's surface. The fact the outer planets currently have rings while the inner planets do not is primarily due to the fact that the outer planets have so many more moons, and therefore more opportunities for them to collide, shatter to form rings. Other differences and potential explanations. Next question. Why do the outer planets spin much faster and orbit more slowly than the inner planets do? The latter is primarily a result of their distance from the sun. Newton's law of gravitation explains that gravitational force is affected by both the mass of the bodies involved and also the distance between them. The Sun's gravitational pull on the outer planets is lessened due to their increased distance. They also obviously have much more distance to cover in order to make a complete revolution around the Sun, but their lower gravitational pull from the Sun leads them to travel more slowly as they cover that distance. As for their rotational periods, scientists are actually not completely certain why the outer planets rotate as quickly as they do. Some, such as planetary scientist Alan Boss, believe that the gas ejected by the Sun when nuclear fusion began likely created angular momentum when it fell on the outer planets. This angular momentum would cause the planets to rotate more and more rapidly as the process continued. Boss 2015. Most of the remaining differences seem rather straightforward. The outer planets are much colder, of course, due to their great distances from the Sun. Orbital velocity decreases with distance f.